Welcome, my dear J26 students. We are on to the new chapter of electromagnetic induction. Sometimes it has been high weightage, but unfortunately, this year it was very low weightage. So we never know. But this chapter is definitely interesting. Plus, in J Advance, a lot of questions come on this, and of course, in other competitive exams too, this chapter is quite important. Now, this chapter is sweet and small, so we'll be trying to finish it up in around 3 lectures. In this particular lecture, we are going to mainly discuss Faraday's law, the equation, flux, and Lenz's law. That is what we are going to completely focus ourselves. Motional EMF and eddy currents, etc., non-conservative fields in the next class. And after that, we'll talk about inductors and inductance. So that's broadly how I have divided the classes. Okay. So hi Aparna, Arya, welcome Sanket, Hebu, welcome Vishal, everybody out here. I hope you guys are great. And yes, the festive season has kicked in with Ganesh Utsav starting tomorrow. And then after that, slowly your midterm exams if you're in 12th. And then Dashera, Navratri, Diwali, Christmas, and the first major festival next year. What is it? After Happy New Year? Your JEE Mains, of course, right? So I hope you guys are ready to celebrate JEE Mains festival. Yeah? No. No, sir, there is nothing to celebrate. Yes. There is nothing to celebrate for JEE Mains. We have to celebrate our results next year. And for that, we need to work very, very hard for JEE Mains. Okay. So after that, you will clear boards and then advance and everything. I'm pretty sure. So for us to celebrate the most important festival of our lifetimes, which is next year's result, I want everybody to be super duper focused and super duper diligent. Give up your luxuries, give up your free time and focus on problem solving, lecture watching, reading, writing. That's all you need to do, isn't it? Hi, Adarsh, Hitendra, welcome everyone out here. Abhiram, please do some PY quiz on NSCP. I'm planning it, definitely. I'm planning it, okay? All right, great. So let's begin with the class. And those of you who do not know me, my name is Captain Shreyas, your physics teacher, training kids, guiding kids, mentoring them for the past 13 years. And before that, I was working in a software IT kind of a firm, engineering firm. Yeah, gave up my job just for you guys. So one day, who knew that you guys will be in front of me and I have to coach you, guide you so that you too become just like one of those IITians and NITians like the past senior batches of yours, right? So let's begin, guys. And I hope you have marked your attendance by liking this video. If you've not done that, please do that. Yeah, come on. I'll give you 2 seconds. Do that. And if you have not yet subscribed, ayo, Govinda, Govinda only. Do it right now. Okay? Right. There you go. Let's start. And yes, there is a link for MVSAT. If you have not yet registered, please register. So what is MVSAT? Looks like you are living under a rock. So it's the Mega Vedantu Scholarship Test. Wow. Who is it for? Is it for only 12th? No, it's for 11th, 10th, 9th, 8th, 13th. That means dropper, everyone. Is it going to be online or offline? It's going to be offline, but later on we'll see if we can conduct it online. It's going to be offline in most of the cities, towns across the country. 4th, 5th, 11th, and 12th, 4 options are there. Register using the link. So, what is the benefit? The moment you register, you will start getting a lot of material, study material. And of course, you get to know where you stand once you give the test, right? A beautiful report card, not just the rank. A lot of parameters are going to be there. And if you want to seek admission, of course, scholarship is there. And something better, well, you are going to get lots of prizes up to a pool of 2 crore rupees, right? So, of course, who wants to miss out on prizes and goodies? So, do register that. The link is there in the description box of this particular video in case you haven't seen that yet. Just any video you go, you're going to see it. See right over here. Go down, smash that like button, guys. You guys need to be reminded again and again. MVSAT register now. Okay, cool. So let's begin with the class. Faraday's experiments and Faraday's law. Yeah, ready guys? Show some energy in the chat box. Okay. Yeah, don't be silent. You have to show that energy. Okay. Yes, because even I'm not well today. Not well as in like I have fever or anything, but I have been working like crazy. I'm sleep deprived, everything, and continuous classes. And even after this, I have a batch. Okay. Right. Ready. So let's talk Faraday's experiment. See, what Faraday did was he wanted to figure out, can I generate electricity using magnets? What Oersted did was he saw whether I can create magnetism using electric current. So just to give you an idea over here, Oersted experiment, Oersted's experiment was electricity, how current and electricity can create magnetism. Magnetism. What Faraday did was the exact opposite. What Faraday has done is exact opposite. From magnetism, can I recreate back that electricity? From electricity to magnetism is used in motors. AC generators, or basically your generator, uses the principles of EMI, that is using magnets, it is able to create electricity which is coming into your houses. This process of generating electricity using magnetism is called as your electromagnetic electromagnetic induction. Electromagnetic induction. This process of creating electricity from magnetism is called as electromagnetic induction. Okay. All right, sir. Fair enough. Now, for that, we need to just revise a quick concept of magnetic flux, although we have done electric flux and all these things before, but just a quick recollection of that. When I say flux, magnetic flux, usually the symbol for that, you can use phi or phi B. B stands for magnetism. Okay. So, say for example, we have been given some kind of an area over here. This is some kind of an area. And through that particular area, I'm seeing some magnetic field lines are piercing through it. Some magnetic field lines are piercing through it. Something like this. Okay. Something like this. All right. So magnetic field lines are piercing through that particular coil area or whatever, some area. So this is my area. This is my magnetic field. Magnetic field. How many field lines pass through that particular area? How many field lines pass through this or cut through this particular area decides the magnetic flux. Decides the magnetic flux. So this flux is indirectly proportional to the field cutting through, the field which is cutting through a surface or through an area. So the definition, the formula exactly is the same as electric flux. So flux is nothing but the magnetic field vector dot producted with the area vector. Dot producted with the area vector. This you will use if it is uniform field. If it is uniform field, then you can use B dot A, which is the same as saying B multiplied by cos theta multiplied by A. B multiplied by cos theta multiplied by A. That is your magnetic flux. Okay, so that is when your field is uniform. Like in this case, it is 100% non-uniform. So uniform field might look probably something, let's say like this. Just showing tilted area. and the area vector will be obviously always perpendicular to the surface, just like in electricity. In Gauss law, we have studied this concept. So this is my area vector, which is always going to be perpendicular to the surface, whichever is there. If there is a coil, if there is a box surface, anything, it could be a cylindrical surface, whatever. So it is always a vector perpendicular to the actual real surface. Bigger area means bigger length, smaller area means smaller length of the vector. And in this particular region, you might have some uniform magnetic field lines, which are probably going like this. So this is your uniform magnetic field line, okay, going like this. All right. So it could be at an angle also. Right now I have shown it in the same direction, but of course it could be at an angle as well, something like this. So just showing it B over here, and whatever angle is there between that, that is theta. Whatever angle is there between magnetic field and area vector, that is basically theta. So this is the formula that you can use for uniform field. But the moment it is non-uniform, then the flux is just given by the integration of the magnetic field at that location, and you take small area vectors. Like for example, over here, you can take a small area vector like this, which I can call it dA vector. And at that local place, the magnetic field strength could be B, which can keep changing. So B dot dA's integration means addition. B into dA will give me a small flux. Integration means you are adding all the fluxes in that small areas in that particular surface. So this is what you can say for non-uniform scenarios. Non-uniform scenarios. Okay, I'm just going to block this off for all of you. Now, try to recollect what is the unit of magnetic flux. If you don't remember or don't know, no worries. I'll help you out. Maybe you would have studied it in 10th grade, hopefully. But if you have not, no worries. I'll tell you. The unit is a Weber. So the unit is a Weber. This is only for magnetic flux. I've seen kids using it for electric flux. No, don't use it. It's only for magnetic flux. A Weber of flux is when a Tesla of magnetic field passes through a meter square of area. Passes through a meter square of area. That is the SI unit of magnetic flux. Simple, easy definitions. Absolutely clear? Thank you so much, Gokulnath. I'm so glad. Yes, Vishal, we have started the lecture. Yes, concentrate. Yep, everyone. Yeah. Now, basically, Faraday's experiments were related to the flux changes indirectly or directly, if you ask me. Like, for example, what he did, he took coil and he connected a voltmeter, ammeter to measure whether there is electricity. He then took a magnet and then he placed the magnet near it. When he placed the magnet near it, do you see the reading of the voltmeter? You might think, sir, if I put a magnet near a coil, it will show some reading. So what even Faraday thought, but nothing happened. He again placed the magnet on the other side, used a strong magnet, he changed the orientation, he added more turns, nothing, no reading was shown. Then accidentally one day what happened is when the magnet was moving, when he was taking the magnet from one place to another, that's when he realized that the reading was shown. And that's when he understood that magnetic field really does not cause electricity, or the magnetic flux, the flow of the field is not causing electricity in this coil. But when that magnet moves, the magnetic field lines passing through the coil is changing. Because when you're close, it's different. When you're far, it's different. So when the flux, the field lines which are passing through that coil change, that phenomena is causing electricity. That's what he understood. That is what this experiment shows. So basically, a stationary, or when even if you, by the way, forget moving the magnet, even if you move the coil, right, then also electricity is produced. Sometimes people might be like, sir, if I move both magnet and the coil, then what will happen? if you move both the magnet and the coil with the same speed, then what will happen? The flux will not change, because whatever line is passing through the coil, that same line will pass after some time also and after some more time also. So the flux won't change. So when there is no relative motion, so when there is no relative motion, there is no electromagnetic induction which happens. But when there is relative motion, when there is a relative motion, then there is electromagnetic induction. The EMI definition, I mentioned it here. Through magnetic effects, you are producing electricity, you are inducing electricity. So there is electromagnetic induction, and you can see the voltmeter is showing some reading. How about replacing the magnet with another coil? Then also the results were found to be consistent. So second experiment is where you put two coils nearby. This coil has no battery, whereas this coil has a battery in it. Remember, these coils are not even touching each other. The moment you turn on the switch, suddenly the current will flow, suddenly there will be magnetic field. Some of these magnetic field lines will cut through the coil of this particular solenoid. So earlier, when the switch was off, there was no flux. Suddenly, when the switch is on, there is flux. So there is a change in the flux because of that on or off motion of that switch here. So that change in the flux caused sudden change in the voltmeter reading, and then you realized, oh, EMI is happening, electromagnetic induction is happening. So again, over here, you can say, as long as the flux doesn't change, flux doesn't change. When does the flux doesn't change? When the switch is on or off. When the switch is on or off, then there is no electromagnetic induction which happens. But when the flux changes, when the flux changes, and when exactly will it change? While turning on or off. While you turn it on or off, that process, when it is happening on to off or off to on, that's when electromagnetic induction is happening in this scenario. And he saw that if you increase the number of turns, then the voltmeter reading increases. If you reduce the number of turns, the voltage produced is also less. He understood that, the number of turns also matter, because if you have a one turn, the field lines will cut once. If you have two turns, that lines will cut two times, generating more flux. So there will be more change in the flux when you have more turns, because the same field lines will cut again in one plane, then again in another plane, again in third plane, like that continuously, which creates more flux. So if there is a small change in the flux here, it will be multiplied across all the coils, thereby producing bigger change in the flux, thereby producing more electricity. That is what happens, observed also and concluded also. Okay, all right. I hope this is absolutely clear. Everyone? Yes, sir. This time, will you show pet animation? Because in road series you did. Yes, I did show. But if you want to see that animation, no issues. I'll show it to you, man. Nothing wrong. All right. So we can see that animation. It's there over here. It's there in FET. I mean, I have shown it multiple times in multiple series. Where the hell did it go? Yeah, physics. Go to physics and you can play with these magnets. Just say electricity magnets, and go to Faraday's law of electromagnetism, Faraday's law. Okay, come on, bro. Open. Yes. So you can take, let's say, a pickup coil or a bar magnet. Let's say we start off with that. This is a bar magnet creating field. As you can see, as long as the bar magnet is stationary, these field lines are also fixed. But the moment you move the bar magnet, the field lines will change. So now, if you go take this bar magnet and move it in this particular coil, you can see the bulb is glowing, electromagnetic induction is happening, wireless energy is being created just by moving this magnet, because the flux through this coil is changing. And you can see, I can change the number of turns. Let's say only one turn is there. So the flux will change only one single time. So there is limited electricity. But if you have some 4-5 loops, now say more electricity will be created. See, the bulb will glow even brighter. You can see the brightness has increased, right? Because more electricity will be created. So that is interesting. Also, you can move the coil, still electricity will be created as long as there is relative motion. But if you move both of them together, then there is no electricity. See, when I move both of them together, then there is no electricity. There could be some small variations because of which it is showing some small voltages, but that's okay. So this is again EMI. You can also see the principle of working of generator now. So if there is a tap, you start the water, the coil will start rotate, sorry, the magnet will start rotating. As the magnet rotates, the flux through this coil will change. Once the flux will increase, once it will decrease, and thereby producing this fluctuating effect of EMI, and the bulb is glowing and turning off and on continuously. So that is how a AC generator basically works. Yeah, there is a turbine, there is a dam, water will fall, it will rotate the magnet, the magnetic flux will change, EMI is being induced, and electricity is generated, which lightens up your house. Understood, my dear students? Yeah, this is standard simulations which you can definitely find on FET. Yes, perfect. Hi Pritija, hi Ramya, welcome aboard. Okay, awesomeness. Now let's formally define it over here, and let's write things down. So let's say, for example, we have this particular area. We have this particular area in which I figure out that there was some flux before versus now there is some changed amount of flux. So whenever flux changes, so a change in flux induces electricity, and he saw that the EMF which is induced, okay, this is very, very important. The EMF which is is induced is directly proportional to the rate of change of flux, rate of the change of the magnetic flux, rate of the change of the magnetic flux. The EMF induced symbol is E and subscript IND. I'm mainly interested in the magnitude. I'm not interested in the sign and all of that. Let's not bother over there. And rate of change of flux, which is d phi by dt. Proportionality constant is 1 in SI unit. Here it was proportional. You might wonder how it became equal to. It became equal to because of SI units, with the way units have been defined. So this is exactly the formula of Faraday's law. EMF induced, the electricity induced in volts, how much voltage is introduced in a coil, is how much flux changed per unit time. If you calculate that, that is going to be the EMF. Very plain and simple. Now, as you can see, this particular coil which is there, that coil itself might have some resistance. That coil itself, the coil resistance might be there. The coil resistance might be some R ohms. So in that case, there will be some current which is induced. The induced current will be the induced EMF divided by the resistance of the coil. Now you can also sometimes figure out how much charge flows just because you move this magnet here and there. How can you find out the charge which flows? Say the logic is current is how much charge will flow, per unit time. Okay, this is the resistance. Induced EMF is how much flux will change per unit time. As you can see very easily that this time and this time has just got cancelled, and what is left is how much charge is flowing. That is how much flux has changed upon the resistance. Direct questions can also come on how much charge has flown, and of course your Ohm's law, I is V by R, is still valid. Okay, current is voltage by resistance. From that only you can get this. Is this absolutely okay, everyone? Perfecto. Yeah, Dakshin, 11 chapters are scheduled, my bro. Tomorrow. My God, Skibidi, I got confused. Yes. See, it is there. Work power energy is there tomorrow, ma'am. Yeah, work power energy is there tomorrow. So see you. Okay. Perfect. Right. Amazing. Now that we have understood here, let me also tell you that there are multiple ways in which you can create electricity, and that is what I want to focus on right now. See, when we look at this formula over here, EMF is d phi by dt. When or how can EMF be induced? How can EMF be induced? Simple answer to that is flux change. Flux change. This is like the overall generic answer. But how will the flux change? If you think closely, then you will realize there are actually three different ways of doing it. There are actually three different ways of doing it. Okay, let's start. Let's go one by one. Okay, let's go one by one. Starting off with the first one. How can you change flux? One option is, because see, the formula for flux, what was the formula for flux? Like I've given over here, BA cos theta. Let's say the magnetic field only is changing. So first variation is, let's say magnetic field is changing. Magnetic field is going to change. Then what happens? Think carefully. Your EMF which is there, which is d phi by dt. So you have d phi by dt. You have B A cos theta. This magnetic field will come out. Sorry, area and cos theta will come out. This entire term of area and cos theta which is there, this entire term will come out because only magnetic field is varying. So you will have A cos theta multiplied by rate at which magnetic field changes. So this is first way of changing the flux by which EMF can be induced. Then the next way is by the area itself changing. Area itself changing. How will that affect? Again, observe carefully. EMF being d by dt of phi being B cos theta into A. B and cos theta hasn't changed, so we can bring it outside the derivative. So it will be nothing but B cos theta into rate at which area change. So maybe you know how fast the area is increasing or decreasing. Maybe the radius is changing of the coil, or maybe you're reshaping that coil. So area changes due to some external factors. So that can also cause flux change and EMF induced. And the final way in which you can create that EMF or the flux change is by changing angle. So the angle itself is changing. So the angle itself is changing, which means your EMF will be d by dt BA cos theta. B and A hasn't changed, so they come outside the derivative. So B and A is outside, and I have d by dt of cos theta. Don't jump and say, sir, derivative of cos theta is minus sine theta. See, this is theta, this is t. You cannot differentiate it like that. You have to use chain rule and all of it. Okay, so be little careful. Don't just jump and say it is minus sine theta. That is wrong. Okay, so these are the three different scenarios that you can ever get. That is all that is there in Faraday's law. Either area will change, or B will change, or angle will change. So we'll see all the kind of scenarios. Okay, one by one. Let's start with some questions. Okay, coming up on your screen. Here it is. A rectangular loop of some length and width is placed at an angle of 60 degrees to the magnetic field. the loop is removed from the field in 10 seconds, the average EMF induced is how much? Very nice question. Okay, let's visualize it first. Okay, we have our loop which is at an angle of 60 degrees to the magnetic field. Okay, length and width both are given to me. Okay, so this is our loop. Let's assume, okay, like this, and it is at an angle of 60 degrees to the magnetic field. It is at an angle of 60 degrees to the magnetic field. The magnetic field is also given to me, which is basically, oops, 4 Tesla. 4 Tesla. Now, as it is mentioned over here, this particular angle is 60 degrees. Angle made by the surface with the magnetic field. Can you think and clearly tell me how much angle will that particular area vector make? How much angle will that area vector make with the magnetic field? Yeah, quickly think and tell me, will it still be 60 degrees? I don't think so, it will be 60 degrees. I mean, just look at the diagram, sideways diagram. This is your magnetic field, which is going like this. Okay, this is your magnetic field, which is going like this. Now, as per the question, this angle is 60 degrees, but the theta which is there in our formula is always the angle made by the area vector with the magnetic field. That is the angle which is very important. So if this is 60, obviously this is 60 degrees. So naturally, how much will this particular angle be? It will be 30 degrees. So theta is 30 degrees. That is one of the most common mistakes which many people do. Yeah, it is not 120 also. Okay, even if you take 120, it is again, on obtuse side, you will unnecessarily get negative signs and all of that. Don't go into those negative signs. It is actually 30 degrees if you notice carefully. Okay, perfecto, sir. What is the average EMF induced? The moment average word comes, I will become little careful. See, instantaneous was just the derivative of the flux with time. But if you ask me what will be the average value of the EMF, it will be big change in the flux upon the total time. Okay, so we have to find the average EMF, not the instantaneous one. This was instantaneous. This is obviously going to be average value. Change in the flux is final minus the initial flux. I'm interested only in the magnitudes. I'm not interested in the signs. So final flux minus initial flux, whole thing divided by the time. Because I have removed it from the field, once it is outside the magnetic field, there is going to be no flux at all. So this flux is just going to be a zero. It's just going to be zero because it has been removed. So 0 minus 5 with the mod symbol, it is just going to be the initial flux by time. But what is that initial flux? It is going to be the magnetic field into area into cos theta, whole thing divided by the time. Now it's just a matter of actually sitting and substituting everything. So magnetic field is 4 Tesla, if I'm not wrong. Area is length into width, which is 2.5 multiplied by 2. Then you have cos of 30 degrees, and the total time in which you remove it is how much seconds? 10 seconds. So now you can do it very easily. 2.5 into 4 is 10. 10 and 10 cancel. So it is 2 into cos 30. Cos 30 is root 3 by 2. So 2 cancel. So it will just become root 3. So it will just become root 3 volts. So it will just become root 3 volts. Root 3 volts. Now it is not matching over here with anything. Forget that. But root 3 volts will be the answer. And root 3 volts approximately is 1.73 volts. 1.73 volts. The closest answer for 1.7 will be 2 volts. Simple. Everybody with me? Understood? Clear? Yes? Yeah. So these options are not matching. Forget about it. But the actual true answer will be 1.73 volts. Moving on to the next question. A coil is placed perpendicular to the magnetic field. Okay. When the field is changed from 3000 change to 3000 in 2 seconds, an EMF is produced. If the diameter is this many meters, then the number of turns in the coil is how much? Okay. Again, you're changing from this field to this field in so much time. EMF is given, number of turns is asked. So again, if you ask me, average EMF is the total change in the flux upon the time taken. Now that average EMF is given, how do we calculate the change in flux? It will be again final flux minus my initial flux. I'm always interested only in the magnitude. Please mind it. I'm never bothered about the direction, or right now at least. Okay. Now, earlier it was 5,000. Later on it became 3,000. So it has essentially reduced because of the magnetic field. So flux is magnetic field final into area, but also number of turns will be there. B into A will be flux through one coil, but there are n number of turns, so n times the flux has to be multiplied. So final flux is this. Initial flux is initial magnetic field into area into n, the whole thing divided by the time, mod value of course. So an is common along with time. So let me just bring it outside, and of course we will just be left with BF minus BI. That is your average EMF. Now it's just a matter of calculations. Average EMF is given to be 22 volts. So put 22 over here. Area is pi into d square by 2, right? Area of a circle is pi d square by 2. How does by d square by 4 actually? Pi r square is the formula. Radius is diameter by 2. So this will become pi d square by 4 actually. Pi d square by 4. So what is the value of pi? What is the value of pi? Value of pi is 22 by 7, and d diameter is 0.02 whole square divided by 4 multiplied by number of turns divided by the time. How much time do you take? I think in 2 seconds. So divided by 2 multiplied by difference of the magnetic fields, which is final minus initial, which is 3000 minus 5000, which is with the mod. So it will become 2000. 22 cancels. I think you will be getting the right answer now after this. What is the answer, my dear warriors, that you are getting? Just try it out. It's not that difficult to see. 22 will cancel. 3000 and 5000, 2000 will be there. That number 2 will cancel with this 2. This 2 square will become 4. 4 will cancel. So it will be a power of 10 if I'm not wrong. Just check this out. Yes, just check if it will be a power of 10. But again, why are the options completely different every single time? I think options are getting mismatched here and there. Just see guys, once again. Oh, sorry, 7 number is there. 7 number is there, so it will be some 7. So this will be 10 to the power minus 4, that is 10 to the power 3. So what will we get over here? Therefore, 1 is equal to 1 by 7 is there. This will be 10 to the power minus 4. This will be 10 to the power 3, and n is also there. Rest everything got cancelled. So n will be equal to 7 into, this is minus 4 and plus 3 minus 1. So minus 1 goes on the other side. So it will become 70. So n is basically 70 units, which is option B. Yes, that is the right answer. Perfect. Okay. Clear? Yes. All right. All right. Perfect. 180. Why will you do? See, whether you measure from this side or that side, it doesn't matter. Cos of 30 degrees is root 3 by 2. You don't have to do 180 minus 90 plus 60 and all of that. Not needed. Okay. Just check it out. I'll just show it to you once more over here. See, don't see area vector. You can take it here also, here also. Okay, fine, not an issue. But take the closest area vector to the magnetic field. That will be easier. You don't have to do that 180 wala headache. So the clear mentioned thing is placed at an angle of 60 degrees to the magnetic field. So the plane of the coil is at 60 degrees. So if you see the side diagram, the plane of the coil is at 60 degrees with the magnetic field. So if this is 60, this is 60, this is 60, the area vector will make 30 degrees. Okay, so that is the reason why I put cos of 30 and not cos of 120 or something like that. Okay, yes. So, Ibu, it is not cos 60, it will be cos 30. See, the rectangular loop is placed at an angle. The loop is made at an angle with the magnetic field, not the perpendicular. So if you look at this diagram, the plane of the coil is at an angle of 60 degrees with the magnetic field. So the area vector will be making the complementary angle. That is a rule of thumb always. So whenever plane makes an angle, the area vector will make complementary angle. Is that okay, Ibu? Yeah. Yes, you can definitely do it, Naxen, and please follow the plan which I have given on the channel. It's just there right over here. I don't know whether you have seen this weekly plan video. I have given a proper Excel sheet with proper details of which chapters to complete when, date wise, actionables, wise also have given how many practice questions you should do, when should you do revision, everything I have given. Please watch this video. It's the best video on the internet for JEE aspirants. Okay. All right. Moving ahead to the next question coming up on your screen. A conducting loop of some radius is placed perpendicular. The magnetic field is decreased to 0 in 0.5 seconds at a steady rate. The induced EMF at 0.25 seconds is how much? Now, tell me one thing. Here, magnetic field again is changing. So, question is how much EMF is going to be generated. So, all that you have to do is EMF is nothing but rate of change of flux. Flux is nothing but B A cos theta. Here B only is changing. So A cos theta will come outside and you will just have dB by dt. Now radius is given, magnetic field of this much is given, the magnetic field is decreased to 0 in 0.5 seconds is given, induced EMF is asked. So first of all, if you ask me the area of the coil, it's right over here. It's a circular coil. Area is going to be pi r square. Pi is 3.14, I can say. 3.14, 22 might not be needed, hopefully. Okay, radius is, oh, I don't even need that value. I can just leave it as pi because I can just see radius is 10 by root pi. So this is 10 by root pi, but this is in centimeter. So 10 to the power minus 2 meters. That's it. So when you square it, root pi square and pi will get cancelled. This is 10 to the power minus 1 square, which will be 10 to the power minus 2 meter square. So area will be 10 to the power minus 2 meter square. Another thing mentioned is it is perpendicular to the field. So if this is the coil is perpendicular to the magnetic field. So that means the area vector is parallel. So the angle will be 0 degree. So it will be basically cos of 0, cos of 0 degree. And then finally you have dB by dt term. The magnetic field is going from zero point 0.5 Tesla to 0 in 0.5 seconds. So how much did the magnetic field change? 0.5 Tesla. In how much time? In 0.5 seconds. That's it. So this is basically going to be 1. This is 1. This is 10 to the power minus 2 means 0.01 volts, which is the same as saying 10 into 10 to the power minus 3 volts, which is 10 millivolts. So 10 millivolts, which is option number A, guys. Option number A is the right answer. Is this absolutely clear how we solved this question? Amazing one. Yeah. It will be around 1.5 hours, Priya. Okay. So these are the kind of questions that you usually get in Faraday's law. Let's go to the next one. A coil of certain area and certain turns is rotated with uniform speed in an axis perpendicular to the magnetic field. Flux and the induced EMF E across it at any instant when B is parallel to the plane of the coil are. Interesting question. So, say for example, if you take this particular coil like this, and it is rotating right now. This is our area vector. Okay. And let's say the magnetic field is like this. Let's say the magnetic field is like this. This angle that you see over here, this angle that you see, that angle theta is angular speed into the time, because omega is theta by t. Theta will be omega into t. Omega is the angular speed, t is the time. So with this logic, we are assuming that at t is equal to 0, the area vector was in line with the magnetic field. So at t is equal to 0, basically initially area vector was parallel to the magnetic field. That is what I have assumed. And it is now rotating with some angular velocity. It is now rotating with some angular velocity. So let's try this problem out now. So EMF will be d by dt of the flux. The flux itself, has B, A and cos theta. B and A are constants. Number of turns are also given. So I have to multiply it with N. So B is a constant, A is a constant, N is a constant. So I'm just left with derivative of cos theta. This is the exact same situation which I mentioned over here when I told you there are multiple ways of producing EMF. One of the ways was changing the angle, and you could see this term came over here. Same thing, but there are n terms, so I have to multiply it with n. That's all. Okay. Now going ahead, my EMF will be BAN as it is. This I can't derivate normally because theta and time are two different variables. So I will do one thing. Theta is nothing but omega t, or I could have used chain rule, but that's okay. So it will be now derivative of cos omega t with respect to now d omega t. Deliberately I did it, but omega was never there here. So I need to multiply it with omega. Now I can differentiate this. So therefore, the EMF will be B A this omega and then N, and derivative of cos theta will be minus sine theta. So this will be minus sine of omega t. This is the answer for EMF in general as a function of time. Born sine omega t. Now let's look at the specific question right over here. Okay, this is exactly that scenario, my dear warriors, which I'm just telling you right over here. We already saw these problems where magnetic field was changing. Now we are seeing this problem where angle is changing. Angle is changing. So we are just keeping cos theta inside the derivative. Okay, let's see. The magnetic flux and the induced EMF across it at the instant when magnetic field is parallel to the plane of the coil. When the magnetic field is parallel to the plane of the coil means what? See, the coil would have rotated like this, and the magnetic field is parallel to the plane of the coil. That is what they mean. That means my area vector now will be here. Of course, area vector will be here like this. This will be 90 degrees. Okay, everyone. So if you ask me what is the flux and what is the induced EMF, one by one, let's go. If you ask me the flux value, the flux in this scenario, phi, will be B into A into cos of 90, angle between area and magnetic field. Cos 90 is 0, so the flux will also be 0. So flux is 0 here and here. So B option and D option gets eliminated. Now what about EMF? Think what will be the EMF? Well, in this particular time, what is that angle? Theta is basically 90 degree. So essentially, this omega t is 90 degree or pi by 2. What is sine of 90? Sine of 90 is 1. So the EMF magnitude wise will obviously be BA omega n, because sine 90 is 1. So BA omega n should be there. So here also it is there, here it is not there. So hence option number A. Got it, everyone? Yes, perfecto. Yep. Okay. Right. Yes, Pritija, what a question you have, please let me know. Hello, Yogesh. Welcome aboard. Yes, I think Ibu, your doubt also got cleared regarding that previous question, regarding that confusion. All right. Okay. So that is the correct answer to this particular problem. At an instant when magnetic field is parallel to the plane of the coil, so flux will not be there, but at that moment EMF will be there, because flux might be instantaneously zero, but does not mean that EMF is not there. It's just like at the topmost point, velocity is zero, but acceleration is there. So flux is zero, but before and after the flux was not zero. So it is changing even at that moment. So EMF is still going to be there. Okay. So moving on to the next question on your screen, here it is. There is a square loop of certain dimensions. It is moving at a constant speed and the edge is 50 centimeters wide. Okay. The value of the EMF after 10 seconds is how much? After 10 seconds, how much? The front edge enters the 50 centimeter wide magnetic field at t is equal to 0. Okay, let's think. After 10 seconds, what's the displacement going to be? Displacement is going to be velocity multiplied by time. So what's the velocity? 2. How much is the time? 10. So it will be 20. Is it meters? Yeah, 20 meters. Okay. Displacement is going to be 20 meters. That's crazy, guys. If it is 20 meters, I mean, this coil would be way out of the magnetic field. I mean, the magnetic field will be here and our coil is going to be somewhere else. Our coil will be somewhere here, moving like this. So it is even out of the magnetic field. There is no flux in this region. So if there is no flux, the change in the flux is also zero. The EMF induced is also zero. So hence the answer will be also a big fat zero. Is that absolutely clear, my dear kids? Yeah. Pritija, class 11th impossible to finish by second week of October. Okay, it's not possible only because mechanics, yes, 100% it will be done, because now we are on to work power energy, then circular center of mass collision rotation, that part will be done. Maybe SHM might be done. So mechanics part will be done, and then after that the remaining we'll see how to do it. Okay, cool. Amazing, amazing. Let's do one more question coming up on the screen. It's amazing now. Oh, this is exactly the question I was waiting for. See, guys, I had told you some time back, multiple ways of creating EMF. This we did, this we did, this we didn't do. Now, this kind of problem model I'm showing you, where the area itself changes. Okay, the area itself is going to change. So let's have a look. There is like a loop which is in a field with its plane perpendicular to the field. Somehow the radius starts shrinking at 1 millimeters per second. Find the induced EMF when the radius is 2 centimeters. So the area is shrinking. Field is constant, number of turns is constant, angle is constant. Let's think how to do this question. Simple Faraday's application tells me it should be d phi by dt, but flux, like I know, is magnetic field into area into cos of theta. Now see, the magnetic field lines are perpendicular to the plane. So area vector is also parallel to the field. So area vector and the magnetic field are in the same direction. So angle is 0 degree. So it will be cos of 0 degree. Are there any turns? No, number of turns is 1 only. So cos 0 is 1. B is a constant. So B comes outside and I am just left with dA by dt. That is your EMF. But wait a minute. I know the field, but I don't know at what rate is the area changing. So let me think. If you, by the way, this much part you understood, right? The magnetic field was inside. The magnetic field was inside, and even the area vector, the magnetic field was inside, and even the area vector was in the same direction. That is the only reason why theta was 0. Okay, cool. How do I find the rate of change of area? I have a trick. Area is pi r square because it's a circle. Substitute that particular area over here and see what exactly happens. Therefore, EMF will be B is there. Pi is a constant. So bring that pi dude outside and r square will remain inside. And now you just take the derivative of r square with respect to time. But wait a minute, I can't take the derivative of r square with respect to time like this. It's not allowed. There are two different variables. So I need to differentiate it with respect to dr, and then I need to put dr by dt. Now it kind of makes sense. The pi remains as it is. This is r square. Does it make sense? I have just used chain rule. So now let's see what exactly do we get. Therefore, our EMF will be b pi is there, b into pi is there, dr square by dr, dx square by dx is 2x. So this will be 2 into r, x raised to n formula, and leave that dr by dt as it is. Don't touch it. You can't do anything about it. Now you know all the numbers. Magnetic field is 0.02. Okay. Pi value, I think we'll have to give it in terms of some decimals. So 3.14. 2 is there. When the radius is 2 centimeters, it is clearly mentioned. So R is 2 centimeters, and that's in meters. And dr by dt, rate at which it shrinks, is 1 millimeters per second. So 1 millimeter is 10 to the power minus 3 meters per second. That is it. That is your answer. Solve this and see if you are getting it as 2.5 microvolt. 2.5 microvolt. Okay. So you should get it as 2.5 into 10 to the power minus 6 volts approximately. So therefore, EMF will be 2.5 microvolt. Absolutely fine, my dear warriors. Perfect, perfect. Amazing question. This is where radius is changing, area is changing, flux changing, creating EMF. So these are the only models of Faraday's direct law which you can get. Okay. Now let's go to the Lenz's law. Now this is very straightforward, but if you try to confuse it by some stupid rules, trust me, you will make stupid mistakes, silly mistakes in the exam. So just go by my logic. You will never ever even be confused. Yes, it is procedural, few steps, but you will not make any silly mistakes or not have to remember many things. It's without remembering too many things, you can do it. Okay. Hi, Mahesh Babu. Welcome. Endariki namaskaram, Ammu Vinny. Welcome, everyone. Hi, Chintamukla, welcome. Hi, Patil. Hi, Arya. Thank you so much, guys. Yeah, thank you. Lenz's law. All this while in Faraday's law, we were talking about value of the EMF. We never spoke about the direction of the current or direction of the EMF. Lenz law gives me the direction. Okay, Lenz's law basically gives me the direction. So, what Lenz's law says that Lenz's law basically it is based on the principle of energy conservation. It is based on the principle of energy conservation. It gives the direction of induced EMF or current, induced EMF or current, and it is completely based on the law of conservation of energy. And how you have to apply it is as follows. The direction of the current induced is such that its magnetic field opposes the change opposes the change of the magnetic magnetic flux entering the coil entering the coil. If the flux is if the flux is increasing then the induced field weakens that magnetic field it weakens that magnetic field. And if the flux is decreasing, the flux is decreasing, then the induced field will strengthen it. It will strengthen it. Okay. Now, this is the main theory, concept, definition, law, whatever you can say. Now, let's understand how do we exactly apply it. I'll give you a simple example. Let's say you are studying right now, and then you tell your parents, I want to go out and play. What will they tell you? No, shut up. Come and sit inside and play. Sorry, sit and study. Don't go outside and play. Let's say you are playing outside, and then you tell them, I want to sit and study. They will tell, why? You are playing, no? Chuma, sit outside and play. Don't come inside and study now. Whatever you say, they will oppose. So, if you say that I want to go out with my friends, they'll be like, no, don't go out. If you are already going out and you say, I will come inside, they'll be like, no, don't come inside. It's okay. So, that is exactly what Lenz's law does. It always is opposing whatever changes are happening in it. If by chance the flux which is entering inside is becoming stronger, then the current which will be created inside will create its own magnetic field which will try to weaken it. If the flux which is entering inside is slowly reducing, it will be like, oh, you are reducing, I will help you, and it will strengthen it. The induced field will circulate in such a way that its magnetic field will support the external field. That is the Lenz's law. Let's understand it with examples. Let's understand it with examples. Okay. Let's see one by one. Let's take this particular example right over here. North pole, south pole, north pole, south pole. Okay. Then we can probably flip the poles over here and we can say this is the south pole, this is the north pole, this is the south pole, this is the north pole. Okay. Obviously, the field directions would be slightly different. So I can't use the same arrow marks as before. Okay. Let's see what happens. This is the north pole coming towards the coil. Okay. This is the north pole which is coming towards the coil. I also need to show the central line so that you don't get confused. Okay. Now observe this. Carefully you have to see. Okay. Carefully you have to see. Now I'll just get a coil so that you can understand it. So just getting a coil for all of you. So this coil is like this, okay, right over here, just imagine. And there is a north pole which is coming towards it. What will this coil do? It will say, oh, there is a magnet coming towards me. Whatever happens, it will try to oppose. So it will try to oppose that magnet. How will it try to oppose that magnet? Remember, north pole repels north pole, south pole attracts north pole. So what it will do is this particular coil, it will try to repel this magnet by creating a north pole this side and a south pole this side. Getting my point? So what it will try to do is it will create an induced field such that this north pole is here, south pole is here, and this north and this north, what will they do? They will repel. Why? Because this magnet was coming closer. In order to do this polarities, hold your thumb from south to north. Your fingers will curl like this. So automatically the current direction which is induced, you have obtained. It's so easy. All you have to do is always oppose whatever is happening. Yeah. Yeah. Can I darken that axis? Oh, sure, sure, sure. Why not? I think it is not so visible. Why not? I'll just darken that axis. Okay, I hope Evo now it is clearly seen. Now let's look at the second scenario. In the second scenario, the magnet is going away. So imagine from this particular coil, this magnet is going away. The Lenz law says whatever is happening, you have to oppose, strictly oppose. That's it. Don't think too much. So to oppose, what will you do? North pole is going away. So you will create a south pole here and the north pole on this side. South pole this side, north pole back side. So this south and north, what will happen? They will attract each other. It will prevent its motion. So now they will attract each other. So if south is here, north is here, from south to north, if your finger goes like this through this particular coil, south to north, see how your hands are turning, fingers of the right hand, how they are turning like this, isn't it? How they are turning is like this. So the current now will go in this direction. So this is the direction of the induced current. Understood how to get it? Isn't it very simple? Yes, that's when even if you start today, you can crack JEE Mains. Just follow the timetable which I have given you. Just check my live section. I have given an entire PDF Excel sheet of how exactly to plan physics, chemistry, maths. I'm guaranteeing you, you can easily get 90 percentile even in the first attempt. Forget 90, even you can get 95 percentile. Okay. Next, let's look at the other scenario, which is over here. Okay. In this case, south is here, north is here. Now, what will happen? The south is coming closer to this particular coil. So it will not like it. So it will try to repel it by creating south here, north. So they will essentially repel. They will basically repel. Here, south is moving away. So it will not like it. This coil will pull this magnet by creating a north pole on this side and a south pole on this side. Is that understood? Now, always how your thumb should go from south to north. So this is south, this is north, this side is south, this side is north. So south to north, if my thumb goes like this, my fingers will curl this way. So that is why this will be the direction of the induced current. Again, over here, south to north, my thumb should go like this. As you can see, my fingers are curling this way. So the current will be coming like this. This is the direction of the induced current. Is it now absolutely clear? Everyone? You should focus on the essential chapters first, and then the high weightage, and then the low weightage. So you don't have to break your head. I have already made the chapter list where you don't have to think only what is high weightage, low weightage. You just have to follow this flow. Okay? So please follow this flow. This video I have made it only for you. I have mentioned that Telegram group in which that free download is there. Okay, you can download this PDF sheet as it is. Okay, just use that. All right. Okay. Snap वर येशील का पाटील? My God, flirting. Huh? Oh, I didn't know YouTube also has secondary applications for flirting. Very good. Congratulations. I both I hope both of you enter some random college where you can flirt day in, day out. May you get the same college very soon. A bar magnet is released from the top of a fixed loop as shown. What will be the acceleration of the magnet? You don't have to think only. Guys, this coil is there. If you drop that magnet, as soon as that magnet comes close, this Lenz's law will come into play. It will obviously repel. The moment it repels, can it fall down at G acceleration? No. If it is only a free fall motion, then it is G. This is lesser than free fall. So the acceleration will be less than G. So hence A will be lesser than the acceleration due to gravity. Very simple, easy peasy, lemon squeezy. Moving on to the next question, guys, coming up on your screen. Here it is. Okay. Let's see if you can solve this. A square loop of certain side is moving with a constant velocity v away from an infinite current carrying wire. Find the direction of the current in that loop. Interesting. See, this current carrying wire is there. That current carrying wire is going to create its own magnetic field. The current is going like this, right? So if you hold your thumb, the fingers will curl in this direction. So this is how the magnetic field will be. Magnetic field will be. As you can see, when you are close, the magnetic field will be very, very strong. But when you go away, then the magnetic field is going to become slightly weaker. And as you go further away, it's going to become even weaker and then weaker, and so on and so forth. So, as you can see, this particular coil which is there, from here to here, there is strong field. So there is strong field when it is closer, versus when it goes away, the field is weak. So there is weak flux, smaller flux as such. So can I say from here to here, the flux has reduced, the flux has reduced, the flux has reduced, everybody? And what does Lenz's law say? We have just seen it right over here. Whenever the flux reduces, magnetic field is created to help it, to strengthen it. So, going over here, yes, to strengthen it, magnetic field has to be strengthened. So, you need to create an induced field in the inward direction. So, induced field will be like this, which means your thumb should go inside, the fingers will go like this. So, the current will be in this direction. Which direction is this? Clockwise. So, option B will be the right answer. Yes, perfect. Clockwise is the correct answer. Understood, my dear warriors? Very simple. So current here will be like this. You don't have to think at all. The logic is very straightforward. No memorizing anything. It's just opposing, opposing, opposing. That's all. Moving on to another question coming up on your screen. Here it is. Two coils A and B are placed coaxially, same distance. When the coil A in which DC current is flowing is moved towards the coil B, then what will happen? Both coils have currents coaxial. Two coils A and B are placed coaxially. Okay, let's think about it. There is this coil over here, and then there is this coil over here. Coaxially means like this. Okay, now some distance in the coil in which DC current is flowing, coil A in which DC current is flowing is moved towards the coil number B, what will happen? Very interesting question. Come on, my dear students. First of all, this coil will create its own magnetic field. The magnetic field lines will probably look something like this. Something like this. So earlier some flux was passing through it. As you can see right over here, there is some bit of flux which is piercing through that particular loop. So when this particular coil comes closer, what will happen? The flux in this direction will increase. The flux will increase in this direction. Agree or disagree? The flux will increase in this direction because this line which was missing this coil will now pass through that coil. More flux will go through that coil. So if the flux increases, you should always oppose it. So how do I oppose? Induced magnetic field will be in this direction. Induced magnetic field will be in this direction. You're just following Lenz's law. Where did it go? You're just following Lenz's law right over here. If the flux increases, magnetic field will try to weaken it. If it decreases, it will try to strengthen it. That's all. Simple. So going over here, yep. Okay, so magnetic field is in this direction. So hold your thumb also in this direction. You can see the fingers of your right hand will curl like this. It will curl like so, like this, isn't it? So this is the direction of your induced current. So the current will go like this. The current will go like this. Now, quickly think and tell me, one current is going like this, the other current is going opposite direction. So what happens to opposite currents? What happens to opposite currents? Opposite currents, will they attract or will they repel? In electricity, opposite charges will attract, but in magnetism, opposite currents will repel. So opposite currents will always end up repelling each other. Hence, the answer to that will be coils will repel each other. Yes, option number B. Perfect. There you go. So this is how Lenz's law is used, my dear students. I've given you some really amazing examples through which 100% you will not be confused. Let's see if you have one more example on this. Oh yeah, we have one more example. Let's see. There is a square loop of copper which is going inside a region of uniform magnetic field. Here it is outside, partially inside, completely inside, partially outside, and fully outside. Slowly it is going out. If FA, FB, FC, FD are the forces that should be applied to keep it moving with some speed, can you compare these forces? Can you compare these forces? First of all, when it is completely outside, then there is no flux. Look at it. When it is completely outside or when it is completely inside, here so there is full flux. The point is, whatever the flux is, here the flux is 0, here the field is non-zero, but the flux is going to be constant. Here also the flux is going to be constant. Why? If you go from here to here, nothing was there, nothing will be there. From here to here, whatever field lines are here, same field lines will be there. It's a uniform field. So flux wise, there is no change. So whenever flux is constant, the EMF, the EMF will be 0. So here also the EMF will be 0, which means the current will be 0. Okay, current will be 0. If current is 0, ILB will be 0. And what is this ILB? ILB is the force on that wire. So hence the force will also be 0 here. Force will also be 0 here. Got it, my dear warriors? Force will be 0 in both these places. But Sonali, this is an English medium channel, my dear. We already have hundreds of Hindi medium channels. There is barely one channel, I think, one or two channels, but some channels don't even focus on JEE, or some channels come, go, God knows. So when there is one channel in English, and that too I'm not talking very high level English, very laddu English, Indian English I'm talking, and deliberately I will talk like that because I want everybody to understand. It's not that I'm showing off my English skills over here. I want people to understand my physics, not English. English is just a medium of communication. That's all. Okay. So what about this scenario? Here flux is increasing, here flux is decreasing. As this loop goes inside, more lines will go. As the loop goes outside, less lines will go. So in this region, flux is not constant. In this region also, flux is not constant. The moment flux is changing, obviously EMF is not 0. Obviously EMF is there. So current is also there. And the moment current is there, force is also there. Here also force is there. So 0 force, force, 0 force, force. A and C, the force is same. A and C force is same. B and D also, the force is going to be the same. That's it. B and D force is same. A and C, the force is same. Correct. Perfectly fine. 0 equals to 0. Non-zero equals to that non-zero. The magnitudes are going to be the same. Okay. I hope this is absolutely understood, my dear students. So that was the last question which we had. And after this, we are going to go to motional EMF in the next class. We are going to see, eddy currents and all of it. And then we will go to inductors and inductance in the final lecture. Okay. I hope you enjoyed today's lecture. The PDF will be shared as a link in the description box, as well as in the comments. It will be pinned over there. So please download it. If you have not yet created your free account in Vedantu, please create so that you can easily download all the content that we share free of cost. If you have not yet subscribed, looks like you are not serious. So please subscribe. And if you have not marked your attendance, that means you have not yet given your Guru Dakshina, and it is very important for you to give that every single class. So comment below how was the class, and let me know if you have any more doubts or anything else to be answered. I will definitely keep making those videos. Thank you for liking. Thank you for subscribing. This was Captain Shreyas signing off. Bye bye.